In this lesson, we'll examine one aspect of the kinetic molecular theory, number 5. The average kinetic energy of gas particles is directly related to temperature. We're going to do this by examining the Maxwell-Boltzmann distribution diagrams. In a Maxwell-Boltzmann distribution curve, what we're looking at is a distribution of molecular speeds. To start, what we're going to do is use an analogy to help us to understand the information that is given in these diagrams and to give us a sense of an example that we can use to relate this to. So on the side here, you can see I've got a graph started of the number of cars versus the speed. And as the title states, this is going to be an analogy looking at the study of speeds of cars driving on the 401. And so what we want to do is imagine for a moment we're kind of in a helicopter overlooking the entire 401, and we are monitoring and tracking the speed of each individual car at a given moment of time. Okay, and as someone who's maybe been on the 401 before, this highway, you can kind of see that, in general, there's this average flow of traffic where most of the cars are going at a certain speed, but not everybody's going at the same speed. And this is the same case with gases in a container. Not all of the molecules are going to be going at the same speed at a given moment of time. And so what we can do is track this. And so we can kind of think about in this graph what information we would be getting is for every car we would record its speed. So you can almost think about it like a bar graph being developed. So say I have a lot of cars at this speed, and I'm just going to do a few of them. But you can imagine at every single speed, I could draw these little X's to represent the number of cars that are going at that particular speed at a given moment in time. Okay? And what you're going to see is if you have an average speed, so say, it's not rush hour and the average speed at the moment is about 100 kilometers an hour, we're going to get this nice distribution of the speeds, and we're going to have a significant number that are in and around this average. And then we're going to have some outliers both going slow and outliers going fast. We've got those people kind of zipping in and around all of the other cars, and then we might have a stalled vehicle, or we might have somebody who's having a terrible time merging and is basically not moving at all. So if we take this information and then draw a curve to represent along the data, we have what's called a distribution curve. Okay, so if you look over here in this example where we're studying this gas of nitrogen, what we're looking at is at various temperatures what the distribution looks like. So you can see with this first example, we've got at 100 Kelvin, a Kelvin is a unit of temperature, so that's at minus 173 degrees Celsius. We'll learn about that later. And then we've got a second distribution at 300 Kelvin and then at 700 Kelvin. Okay, and so this is, what is our average here? In our car example, our average is 100 kilometers an hour. Okay? So what we want to do is think about how these temperatures impact our distribution. So much like the flow of traffic might change, so with this initial example, I'm talking about 100 kilometers an hour. So if this is the average is 100 kilometers an hour. So this is, at noon. Okay. If I wanted to do the same thing and I wanted to look at a time that's in the middle of the night, so maybe assuming that there's the same number of cars for some reason in the middle of the night, and if the average has changed to either less or more, that's going to change the distribution. Now, one of the key things, though, is that when we change the average, we still have the same number of cars. So with this example here, even though I change the temperature, I'm still going to have the same number of molecules that I am referring to. So what happens is this area under the curve, which represents the number of molecules that I'm talking about, is not going to change. So that's why it's not a shift. Okay, so I don't just move the graph over, but rather I stretch it. So I want to think about taking this end, think of it as a piece of string, and I'm pulling it across and changing the distribution. So if I take this at 100 kelvins and I pull on it to over here, I'm going to get this new distribution of the speeds of the gas molecules in the sample. And then if I increase the temperature even further, I'm going to pull that even further and change the distribution. So change the number of molecules that have a given speed at that moment in time. And the speed that they have is related to the kinetic energy that's available. So as you know, if there's more kinetic energy available, then things are going to be moving faster. So that's why when we have a higher temperature, we're going to have a higher average temperature. The other piece of this is to consider is to look at different gas molecules. So in this example here, we're looking at chlorine versus nitrogen versus helium. And they're all at the same temperature. So if they're at the same temperature, then the same average kinetic energy is available to be distributed amongst those molecules to give them their speed. However, because they're different molecules, they're going to be moving at different speeds. And at the moment, we'll look at this qualitatively, but in the next lesson, when we examine Graham's law, we'll look at this quantitatively. So what we can see here in this example, chlorine, which has a higher molar mass of 70.90 versus helium, which has a molar mass of about 4 grams per mole, you can see that on average, the helium atoms at this temperature are going to be moving faster than the chlorine molecules. And that's simply because of their mass. The little thing that I think about is, imagine two people running around a track. The person who's a bit lighter, they have the same amount of energy available. The person who's a little bit lighter is going to be able to run a little bit faster.